Hello and welcome to Numeristical. We are continuing our series on the fundamentals of gradient boosting. This is the third video in the series, and this is where we're really going to finally present the actual gradient boosting algorithm. So in the previous video, we talked about random forests, and we talked about how we build a collection of decision trees and find clever ways to inject randomness into that process so that that ensemble of trees does a much better job of prediction than a single tree alone would. In this video, we're going to talk about gradient boosting. In this approach, we also build a forest of trees, but each tree tries to improve on the previous collection of trees, and that's what makes it more powerful. So we're really going to get into the details. We're going to understand where does the gradient come in, why this is a sensible thing to do. So if you really wanted to understand gradient boosting inside and out, this is a great video to watch, so I hope you'll enjoy it. Before we get started, I'd like to ask you, as always, if you could please like the video and subscribe to the channel, because that really helps me out a lot. And with that said, let's get into the video. Now we're going to start talking about the gradient boosting algorithm itself and really get in the details and explain exactly how it works. To start though, let's give a little bit of history of gradient boosting and to understand where the terminology comes from and kind of how the idea evolved. So when we say gradient boosting, nowadays we typically mean gradient boosted decision trees, or perhaps even more accurately, a forest of gradient boosted decision trees. But that takes a long time to say, so we typically just say gradient boosting. Now, boosting, that word initially referred to a very particular process where you would fit a model. Originally it was a classification model. And then you would look at which points did my model classify correctly, which ones did it classify incorrectly, and you would add weight to the training points that were incorrectly classified. So you'd look at the ones, which ones did my model get wrong? Let me give more weight to those. Then you would refit a second model on this new weighted data. So then you build the model again and say, hey, pay more attention to these things that you got wrong last time. And then you would add the second model to the previous model. And you could repeat this process over and over again. So you would then look at your new model and say, hey, what did this model get wrong? Let me boost the weights of those. So you came from the idea that you're boosting the weight on the mistakes to give incentive to get them right the next time. So the idea was eventually, hopefully, you could get everything right if you keep making it increasingly more of a penalty for getting particular points wrong. So AdaBoost was an early example of a boosting algorithm. And they found that using a decision tree as the base learner worked particularly well. So what I just described previously, you could use any model that does classification and do the boosting process. But they found that decision trees worked particularly well in this process. Then people analyzed this AdaBoost algorithm and they realized that it was equivalent to fitting the base learner to the gradient of an exponential loss function. So this process where you're boosting the weight on the things you got wrong, if you redo the math, it turns out this is the same as fitting it to the gradient of an exponential loss function. So they said, that's really interesting. We could generalize this then. What if we didn't use an exponential loss function? We could fit the gradient of some other loss function. And that's where the idea of gradient boosting came from. The idea is that you can pick your loss function and then you're going to fit the gradient of it with these subsequent models. So why the gradient? So imagine that you're working on a regression problem and you've got a model that performs reasonably well, but you'd like to improve it. You'd like to get a better model. So you first measure the residuals of your model on the training set. Now the residuals, we mean what's the difference between the true answer and the predicted answer. So when the residual is positive, in this case, it means that you underpredicted the true quantity. And when it's negative, it means you overpredicted the true quantity. And you're going to try to now create a second model using the same predictors that tries to predict the residuals of the first model. So in other words, you want to build a model that can predict the degree of under or over prediction of the first model. So in theory, if you're successful, if you can predict these even with a reasonable degree of accuracy, you can add this correction model to the first model and you get a better model. You don't have to predict the residuals perfectly, but if you predict them with any sort of power, then you can add it and get an improved model. Now, in reality, when we do this, we need to be concerned with overfitting, right? Because suppose that our residuals, our original model is really as good as you can do, and everything else is just random noise. When we fit the second model, there's nothing to predict other than noise. But if you've got a lot of predictors and you've got a sort of complex model, that complicated model might pick up on noise and fit the noise and have a model which predicts the noise terms of the first model, but when you use it on any further model, predicts the noise on the training set, but when you make predictions on a new test set, it's not going to have any added power. So there are various regularization techniques, most of which we'll get into later, that you do to avoid this overfitting. But the most basic thing we do to avoid overfitting is when we add in the second model, we're going to multiply it by a small fraction. So something like 0.05, 0.01, sometimes it's even 0.1, sometimes it's as small as 0.001. But we're going to multiply the second model by this small fraction. So instead of adding the full value of the second model, we're just going to take a small step in that direction. And this is called the learning rate, or the step size, this multiplicative factor. And now we could repeat this process. So now we had our original model, we calculated the residuals, we created a model to predict those residuals, we multiplied it by a small fraction, added it to our first model. Now that's our current model. We can repeat this process. Let's look at the residuals of this new model and see how far off it is, and repeat the process. And since we're doing this over and over again, it doesn't really hurt to take small steps. It means I'll have to take more steps and build more trees, but it's not crucial that you jump to the right answer immediately, or you jump to the best answer immediately. And as I said, there are many other techniques that we'll use to avoid overfitting, and we'll discuss those later in the class. Now, another thing to think about with this process is you actually don't need to start with a reasonable model. You could even start with a completely naive model. You could predict 0 for everything. You could predict the mean, just the overall mean of your data set as a starting point. And this process will still gradually improve your model over and over again. So that's roughly how gradient boosting works. Now, there are a bunch of details, though, that I've glossed over, and so I'm going to go through those now. So what I just described was a very specific version of gradient boosting, and in fact, it was specific to a regression problem with mean squared error loss. Now, why is the mean squared error loss important? Well, with mean squared error, the derivative of the loss function with respect to your prediction is exactly the residual times a constant of 2. So let's just see that. So if you go back to, this might be one of the earliest partial derivatives we've ever done. I'm taking the derivative of the loss function. So the mean squared error loss function is this y true minus y pred squared. And we're trying to say, how would our loss change as we vary our prediction? Should I have made my prediction bigger or smaller? What would happen to my loss? And you see, if you do this derivative, you simply end up with 2 times y true minus y pred. Y true minus y pred, as we said, is the residual, times a constant of 2. That constant ends up not mattering, gets absorbed into that learning rate. So the way to think about it is with mean squared error, the gradient of the loss function is more or less exactly the residual. It's proportional to the residual. So predicting, this is the equivalent, and this is the key to gradient boosting, is these notions are all the same. The residual, the degree of under or over prediction, and the gradient of the loss function. These are in some ways all very similar notions that get tied together. And the proper generalization to think about, the one that is the most general and the most applicable, is the gradient of the loss function. The gradient of the loss function tells you how much I'll improve my loss function by making my prediction a little bit bigger or a little bit smaller. And so when I've got a set of points that maybe all fell into the same leaf of the same tree, and I want to know what value should I assign to that leaf, we can say, well, 9 of the points want to get bigger and 1 of them wants to get smaller. And here's the degrees by which, the magnitudes of these gradients, the degree to which they want to get bigger or smaller. And from that I can do the math to say, here's the value of the leaf that will give me the best improvement of the loss function. So in general, the key concept to get in your head is that the gradient represents the degree of under or over prediction. The sign is what tells you the direction of the mistake. Did I underpredict or did I overpredict? And the magnitude represents the severity of the mistake. And this is particularly true if you have a convex loss function, which is typically the case. When you've got a convex loss function, the gradients get steeper as you get further and further away. So overall, you can think of this process as doing gradient descent on trees, with trees. So each step you take, you build a tree and you take a step in the direction of that tree. And you build a tree that best fits the gradient of the loss function. Okay, so now we're going to go through in a lot more detail with some math and some equations how this algorithm works. Let M0 be your current model. And again, to start out, this could just be a very naive model where you just predict the mean for everything or predict 0 for everything. If it's a classification model, it could be something where you predict just 0.5, yes or no for every prediction. So now let Y0 be the predictions of M0 on your training set. So in a regression problem, these Y0s are going to be numbers, numerical predictions. On a classification problem, these are going to be the probability of being in the positive class. And for now, we're going to just focus on binary classification. Let YT be the true answers on the training set. And let L of YT comma YP be your loss function. So this is what tells you, okay, how much penalty do I pay when the true answer was YT and my prediction was YP. YT are going to be 1, 0 if you're doing a binary classification, or they're going to be the numerical answer. So again, we do this math. If you take, we're going to just write L prime of YT comma YP. We're going to use that notation to represent the partial derivative of the loss function with respect to your prediction. So again, we're saying, would I improve if I made YP a little bigger, would I improve my loss function or make it worse? And then if I'm going to make it worse, that means that making it smaller would improve my loss function. So it's saying, what direction do I want to go in with this particular prediction to improve my loss function? And how much a difference would it make? If it would make a very small difference, then it doesn't really give us that much benefit. And we'd have to trade that off against the other points in that leaf that maybe very strongly want to go in a different direction. And we compute this L prime of YT comma YP. We compute this across Y0 on our current predictions. So we've got our current model, we've got our current predictions, and now we've got the degree to which we would like to make those predictions bigger or smaller based on our loss function. So that's this Z0. It's the degree of under or over prediction, how badly we want to make these things bigger or smaller. And now we fit a tree, call it T1, to predict Z0. And after we fit this tree, we let M1, our next model, be the previous model plus epsilon times T1. So we've got this tree that helps move us, does its best job to move us in a direction that decreases our loss on the training set. And we take a small step in the direction of that and create a new model, M1. And then we could repeat this. Now M1 is our current model. We go through all these steps again with M1.
to build a new tree T2. So let's talk a little bit about how gradient boosting differs from the random forest and why, in fact, gradient boosting is more powerful. So when tuned appropriately, if we get all these hyperparameters right, and we'll talk about those in the next section, gradient boosting typically will do better than a random forest. Now why? Let's do a thought experiment to think through why this might be the case. So imagine we've got a house price prediction problem. And suppose that a fireplace is always worth $2,000. So in the world of houses, if you had the same exact house with and without a fireplace, you'd always get exactly $2,000 more for the house with the fireplace than without. And the idea is that $2,000 is a pretty small amount against the magnitude of house prices. So it's hard for this effect to really show itself because we're not going to have the exact same house with and without a fireplace. The fireplaces are kind of distributed across houses somewhat randomly. So this value of the fireplace is only apparent when comparing very similar houses. Otherwise, it gets lost in the noise of all the other more important factors like the square footage of the house, the age of the house, the size of the lot, and so forth. So now think about how the random forest is going to work. When you start building these trees, at the beginning it's going to be really focused on things like the square footage, the age of the house, the lot size. These big factors are going to really determine the splits at the top of this tree, because those factors are going to have much more, explain much more of the variance than just fireplace versus not fireplace, because fireplace versus not fireplace are going to have a whole set of very different looking houses that have a fireplace and a whole set of very different houses that don't have a fireplace. It's not clear that that $2,000 advantage is going to outplay just the noise of selection of which houses happen to have fireplaces and not. Now, once we've controlled, as we split on square foot, age, lot size, we're going to split on those probably multiple times. Now we're near the bottom of the tree. Our data is now split up across all of these different nodes. And there's basically not very much data left to conclude that the fireplace is better than the non-fireplace, because now we're down to very few data points in each node, and it's hard to have kind of the significance, the power to show that, oh, if you split on fireplace in each of these nodes, you'd get $2,000 extra. You might have leaves that have no houses with fireplaces. Now compare that to gradient boosting. Gradient boosting, we're going to build this forest, right? And at the beginning, we'll start controlling for the square foot, the age, the lot size. At a certain point, we'll have a model that already has controlled for the square footage, the age, the lot size. And now we're going to build a new tree. And what should happen is once you've controlled for all these other things, I've got a model that controls for everything. I look at the predictions that this model is making, and I should notice a pattern that we tended to underpredict the houses with fireplaces a little bit, and we tended to overpredict the houses without fireplaces a little bit. And so now I have the whole data set, and I can see, oh, I'm underpredicting on houses with fireplaces. I'm overpredicting on houses without them. And I can look at that whole thing, and what should happen is now at the top, we should clearly see, oh, fireplaces I'm overpredicting. Fireplaces I'm underpredicting. Without a fireplace, I'm overpredicting. And it should be able to capture that very easily because it has access to the entire data set to make that judgment. So in the next step, we can use all of the data because we're doing this progressive thing. The random forest, the problem is you're always starting from scratch at the beginning, so you've always got to explain all the big things. By the time you explain all the big things, your data about the small things is spread out amongst all the leaves. And you never get a chance to kind of reassemble all that data and fix that problem.
Hope you enjoyed that. In the next video, we're going to talk about the hyperparameters. We're going to go really into detail about all the various different hyperparameters involved in the gradient boosting algorithm and how to tune them and which are more important and which are less important, and talk a little bit about some strategies about how you might get into approaching how to tune them. So I hope you'll join me for that. Before I go, I'd like to ask you again one last time if you could please like the video, subscribe to the channel, it really helps me out. Other than that, have a great day, and I hope to see you watching the next video.